Thanks a lot for the kind introduction. Thanks a lot for invitation here to talk. It has been a long journey with Korea. I started cooperation already in 2016 with some of you. So the presentation today, I will talk about, say, another angle to see what we can do with 6G. And actually, I would like to drive you back almost 100 years ago, when the visionary Nikola Tesla stated when the wireless is perfectly applied, the whole Earth will be converted into a huge brain. But the good news, if we do as engineers the good job, by 2030, by delivering and standardizing 6G, this dream can be a reality. So let me allow to use one single equation, it was a very classic one for some of the engineers, and let me try to see together what we have been doing since 2G in designing a wireless communication system. So we have been targeting to have as much as possible capacity in our system and how we achieve this capacity. So this capacity actually is composition of the channel bandwidth you have times the number of uncorrelated paths we can use for the communication times something which is proportional to the signal to noise plus interference ratio. That means actually the quality of the signal, the power of the signal received at the receiver. So actually what we did, for example, in 5G to achieve actually the factor of 1,000 improvement according to what we had in 4G, we compound 3 gains, roughly targeting a factor of 10 for each one. The first one in terms of radio channel bandwidth improvement by mainly doing different spectrum management, by doing carrier aggregation, that was very important, and by exploring new spectrum, specifically in the millimeter wave spectrum. Who works on the realization of such approach in 5G, sorry, realized actually that there's a lot of challenge there. Some of those are not solved, for which actually we know that, for example, the millimeter wave communication is not full reality for the mobile terminals at least. Then actually the other part was actually improving the number of uncorrelated paths for the communication. And we went to the MIMO, massive MIMO, either ultra-massive MIMO in some case, and we also went to the path for network densification, something we already explored so between in 4G, they were actually one of the major drivers to achieve the capacity, and the use of small cell, and we just, start exploring the use of reconfigurable intelligent surfaces there. Then the third part was about improving the spectral efficiency of the communication, something we have been doing since 2G, which start being tougher and tougher because the smart ideas have already been posed, so now it's more challenging. And roughly working, exploring the thing we're using higher frequency. We have indeed smaller antennas we can embed in the same surface. We can have narrow beams, but we can also have higher dBi antenna gains. But of course, with the problem that the narrower is the beam, the more precise you need to be in the pointing phase to the two antennas. So when you start having mobility, this comes to be a very big problem, for which at the end, some of this gain is challenging to have in reality. Then we also explore new modulation coding schemes, new waveforms, and also again here the use of RS. So this drive to something that this is a table I extract from a paper I wrote some years ago, but actually the division we have in going from 5G to 6G, there are specific KPIs. And what I want to insist is not the specific KPIs, but actually there are 2 families of KPIs we can consider. One is the family of KPIs we use to improve the system performance from 5G to 6G. Roughly, those are the KPIs we justify to have new customers. Why we're spending money for building a new network, why we're spending money for having a new access to the systems. And actually, those are improvement of factor of 10, 100, 1,000, for example, in terms of capacity, in terms of reduction of latency, and so on. But then there's entirely new family of KPIs who actually are meant to support the connect, computation, and intertwining of intelligence in the network, human and artificials. to extend the connect, compute, store, and control capabilities to non-terrestrial networks. And I would say in general to address sustainability of the technology, of the network operation, of the inference in general, the task we want to accomplish, and also in the support of AI. And in this direction, there are at least two major KPIs of our interest. First of all, measuring the energy we consume, not anymore at bit per joule, or how much it costs to transmit a bit, but actually how much the information I carry on the other side is useful, and how much energy I use to process information, to transmit information to achieve a goal. So at the end, you are much more selective on what you want to transfer. You don't need to transfer all the data, and actually you go direct to the one is needed for the goal. And the second part is actually this reliability. That has been a big challenge. At the moment, I can say we didn't meet with 5G, having target in 6G either at order of 10⁻⁹ of error rates. Actually, is not anymore needed if we have artificial intelligence, but we want to have is the inference reliability. How much after receiving data and processing the data we are precise in understanding what happened. And actually this relaxes a lot the errors we can accept at the physical layer. So we have been building generation, and also some of the things we're doing in 6G is building generation as a content-blind communication system, where actually the transmitter, the receiver ignore each other. So let's say that I use my telephone every time with the same Wi-Fi access point in my place, but every time my telephone access point establish communication as they never interact with each other. So this is a waste of previous knowledge, plus the communication itself as a meaning, as a goal. So actually, today we are building this communication as a blind system, as if you are tapping randomly on the keyboard digits and try to be as much precise as possible. But at the end, you don't have a clue about what you're doing. So in this direction, there are at least three major pillars of technology we have been exploring in 6G. So the use of sub-terrestrial communication systems, where we go for higher spectrum, but we either enhance the nightmare in terms of how we do with the real hardware. You can see here in a small picture that actually, if you look about the solution technology we can use for sub-terrestrial communication, we see there are problems in producing output power needed, but also there are frequency, for example, here between 180 gigahertz and 250 gigahertz, for which at today we do not have a sustainable technology that can be process engineered to produce that kind of output power at that frequency. So today, we're still on the dream of the system level, but we are not really considered hardware that can really work on all these frequencies. So there is a problem that this is not a free meal going up in the frequency. Second part is integrated communication and sensing. That's a very promising approach with a lot of investment. Here, there's also a lot of demonstration outside. And then there's the use of new materials, and I would say what we can call generically the reconfigurable intelligent surfaces, where actually we change somehow the pinging electromagnetic fields in the system, try to shape the propagation environment. But all these things are actually very complex and need very complex optimization, for which we do work on using AI and machine learning to optimize how we process the data, how we process the transmission, and also how we operate the network and orchestrate the user resources. Now, let's take the angle from a different point of view. Do we need, again, a factor 1,000 in this capacity enhancement? Or shall we now work on provide application-grade reliability, for example, for the inference reliability, sustainability, and have a system which is AD native. So it works because there are reasoning engine exchanging together. So it's not blind anymore. So the good news, there are at least three paradigm shifts we can explore here. The first one is what we call the goal-oriented communications. So instead of having data-oriented and content-blind communication, we actually have a goal which is established in the cooperation between the transmitter and the receiver, for which at the end we shape the communication, we protect the bit, we select what we send, because those are useful for achieving a goal. So we can, for example, accept the sum of the bits we send with error, we don't care at the end. But actually, the important ones are protected, and we choose also the right information. Second point is the use of, for example, RS, reconfigurable intelligence phases, for doing what we call the wireless communication environment shaping. Here, instead of doing, as we have been doing all the time, of fighting the uncontrollable, let's call dictate by nature propagation environment, we do actually engineer and shape on the demand, on the need, favorable, useful wireless communication environment with the reconfigurable intelligence phase to boost the capacity, to reduce the energy consumption, to reduce the electromagnetic field radiation, to improve the localization precision, and so on. And third, the third point, which is key when using AI, is what we call the A-native semantic communication, where instead of moving and transferring data blindly from one point to another, we take into account there's an AI that can extract useful knowledge and information for a receiver that has to do something with or understand something. So actually, we share only what cannot be deduced or inferred by the receiver via AI or via generative AI, with or without established goal. So using this approach, and those actually are a list of different projects which I either coordinate personally or we work in my group that actually work on the different topic I present. And please let me insist on the topic number 2, number 3. There's also this SIG Arrow project, which actually is a collaboration between Europe and Korea, which I'm honored to coordinate from the European side. I will present briefly, and that actually will face exactly this problem in the coming 3 years. So, given this angle, we can have a semantic-aware SIG technology pillars, where, for example, what we do for the subterrestrial communication, what we do semantic compensation technique of the hardware. So we change the way we conceive the hardware also because we're able to do some kind of AI-related and semantic-related compensation. We do, for example, in the ISAC, what we do, we can, instead of just fusioning information, we can do semantic fusioning and enable to enhance the information we receive. On the semantic intelligence surfaces, actually what we can do, thanks to the fact that we have a joint logical semantic channel and the physical wired channel that work together, we can actually, I will show you some results, use less surfaces, less antenna for the same results. And then, of course, the fourth pillar was not present before, is the use of generative AI at the edge or not, and the semantic AI intertwining. That means actually you have cooperation between AI agent, they exchange meaningful information together, and actually they're able to compress and also to train the system while communicating. So you communicate not only to transfer knowledge, but also to keep training the user and extend domain of application. Okay, so just take 1 minute and try to read this text. Tell me if you can read this text. I didn't find the equivalent in Korean. So I know that in some language we have the equivalent I didn't find in Korean. So what is funny here, that roughly you're able to read this text because your brain is able to correctly interpret the sentences. So as far as the first and the last letter are correct one, either if in verse, and if the length of the word roughly is correct, you're able to correct. Why we do not do this in a wireless communication system? Why should not relax the thing that some of the bits can be noisy, but actually there are key parts that have to be there. So this is the key understanding of why we can robustify with a semantic communication and indeed do a lot of compression. So I will give you briefly some experimental results. We've been working on these topics for now 6 years already. And first example is about compression. So most of the time people ask how much compression can do. Actually, the answer is between roughly 200, factor of 200 to a factor of 500. Here I give an example for images. But if you go to video, you can compress much more. We already have experimentation that goes more than 500 factor. And actually, how we do this compression, we extract the information from the data, building a knowledge graph. So roughly a graph where you have nodes and edges, okay? And then, so these already give a first factor of compression, but then each node and edges, because we're using a semantic system, we can robustify the interpretation of the receiver. We can also compress how much we need to use to represent that. So roughly the floating precision we need on these points. And so in this example, we have almost a factor of 200. Then also we have the experiment that while using the communication also for training, we can speed up the learning, the training AI time of about a factor of 23. And last example I give, I also have others, that actually using the semantic aware communication system, when you use an IRS, a reconfigurable intelligence surfaces, you can achieve the same, either better performance at the application layer, for example, in terms of inference reliability, by using roughly between 25 and 30% of the surface of the wireless, of the reconfigurable intelligence surfaces. That means that either you can consume less with the surface, or you can accommodate 3-4 times more users for the same surface. Okay, now I will spend a few minutes presenting you this new project between Korea and Europe. And actually, so we have from Europe side, we have first state members, which actually is France, Germany, Finland, and Italy. And from Asia, it's Korea. It's focused on Korea. So I'm the project coordinator. Aalto University is the technical manager. Intel is the innovation manager. So what we do here? So what we do, we target to establish and design an AI-driven architecture which also enable interoperability between AI network devices, terminals, and the network. And also study and benchmark the effectiveness of semantic communication on AI's native connected computer systems. And why we do that? Because actually we want to improve the performance of devices, optimize them in terms of the quality of experience, complexity, energy efficiency, signaling, and so on. We also want to optimize the AI-driven network performance and enable or contribute to enable the zero-touch networking. We also work on that because we want to support semantic communication for effective and reliable decision-making, so having an application at the end in the loop. And also prove the feasibility, the technical feasibility of the AI native integration with real-world scenarios and real-world data through experimentation. So how we do that? That's, of course, it will be a 3 years of work, but it's a very condensed way. We target to enhance the device performance with AI and machine learning. Mainly, we are focusing on the energy consumption and complexity on running part of this AI on the device. So be able to be exposed to the AI function either by processing a device or by interacting with the network. And also establish the seamless interaction between user terminals and network infrastructure. Also, the joint optimization of the RAN and the core network using AI and machine learning solutions. Leverage also on semantic communication for AI-driven optimization to enhance the AI reasoning and network optimization, because actually, as I said before, communication can be used to train. A train can be used to enhance the reasoning capability of a system while communicating. And also develop experimental testbed and proof of concept platform where actually we target to implement, and I have a slide on that, specific testbed and to demonstrate our innovation. And we have 4 major testbeds. One which is driven by Fraunhofer HHI, which actually it's on semantic aware edge inference. The second was actually it's driven by ETRI on the inference coordination for cross-domain network slicing. Another one which is driven by ETRI again on effectiveness of machine learning and AI physical layer techniques using Open Run, and the first one driven by CA on Edge Intelligent Platform for demonstrating the compression of channel state information and CQI algorithm using AI. So to conclude, I would like to give you a short example of what, for me, it's indeed a semantic communication. Let's consider that you have a couple that have to exchange for, that's a very French example. Let's say to change some piece of bread, okay? So at the first meeting, they don't know each other, and they are very shy to speak to each other. So they introduce each other. They actually ask kindly and probably describe the request. Please, can you share with me a piece of bread on a white plate, and I will carry that with 2 hands and so on. And you thank each other at the end. Then after several months, I would say the beauty of the first moment start disappearing a little bit. And actually, you know each other. You have a brief introduction. And then actually ask with a level of description which is reduced, what you want to have. And then you have a very brief thanks. Then after several years, there's no introduction anymore. You know each other. You expect the other to understand your action. You ask for with a short request. Bread. I don't know, something like that. And there is no thanks at the end. And after a whole life, you're either not able to hear each other anymore, so your sensing capability are kind of slowed down. So you're just able to hear each other and ask with a quick eye contact something. There's no thank, and you just wait for the next request to arrive. So I'd like to thank you for your attention. Of course, I didn't give you all the details, but you can find some more detailed information on this paper. You can contact me. I guess we have not time for questions, so if you have, I'm very pleased to answer your question. Thanks a lot.